an old Far Side cartoon showing a high school classroom, and a kid with his hand raised saying, "Mr. Osborne, may I be excused? My brain is full." And so this is kind of how I'm feeling right now. Maybe some of you are too, but let's see if we can do one more thing here. So let me give you a brief overview of what I'm going to try to talk about. The overall question is, how does the brain's visual system represent the shape, orientation, and location of objects? And I'm going to mostly talk about orientation, a little bit about shape, and only in passing location. I also should say that I'm going to be talking more about high-level vision than low-level vision here. So the question is, with an object like this, how do we represent these sort of things? I'm going to argue for a central role of coordinate system representations that are constructed around virtual axes and representations that relate coordinate systems to one another. In doing so, I'll present some evidence from errors in perceiving and remembering object orientation and shape. So here's how I'm going to try to proceed. First, I'm going to introduce the topic by talking about the notion of mirror image confusion, because this is going to turn out to be central to the evidence that I'm going to talk about. And then I'll lay out the theoretical perspective I mentioned a moment ago and talk about evidence from orientation and shape errors. And finally, I'm going to look a little bit at how the visual system assigns axes to object shape representations. You can see I'm going to touch on a lot of the points that have come up earlier, maybe from a slightly different perspective. So let's start now with mirror image confusion. A number of years ago, actually back in the 1990s, before most of you were born, I carried out a study with a college student who had a really interesting deficit. So this is AH, and she was an undergraduate at Johns Hopkins. She had 20/20 vision, basic visual functions were just fine, no neurological conditions, no evidence of brain injury. Yet she had a remarkable deficit in perceiving the location and orientation of visual stimuli. And in particular, she made these highly systematic mirror image errors. So in location perception, for example, we did many tasks with her, very simple tasks in which we showed her something and asked her in one way or another simply to report where it was. In this example, she looked at a computer monitor, looked at the central dot there, and then an X was presented at one of these four locations. She had to point to the location where the X was or say where it was, like near left or far left. And this, of course, is a trivially easy task, yet she had a great deal of difficulty with it, with error rates approaching 50%. Her errors were very systematic, though. She didn't confuse all the locations. When she made an error with a target presented here, it was always saying that it was here instead, or vice versa. And when it was presented at one of the farther locations, an error was always the other far location. So it's as if she's kind of reflected the location across this central point. Central axis, maybe. In tasks probing her ability to perceive orientation, we also saw mirror image errors. This is a direct copy task in which she was shown a picture. That picture stayed in front of her, and she was simply asked to draw what she saw, to draw a copy of it. And these are typical errors that she made. So with the picture, she's drawn a reasonable facsimile of the shape, yet she's flipped it left or right, and similarly for the giraffe. And I want to emphasize she's done this while she is looking at it. It's not that we took it away and tested her an hour later.
Was she left or right-handed? Was she left or right-handed?
She's right-handed, and before you start thinking about all sorts of hypotheses about left and right, let me tell you that she also made errors with up and down. Okay. Now, this is a pretty, yes?
For the previous task with the X's, so what was did it lie in the fovea, the two closer ones, or were they all shown in the visual periphery?
They were several degrees from central fixation. Okay, so they're clearly very easy to see. And again, this is just an example of many other tasks, including tasks where we took a three-dimensional object on the table and asked her to reach for it, and she will make errors doing that. Okay. All right. Now, mirror image confusion is not something limited to clear deficits like this. It can also be observed in supposedly normal individuals, and although not in perception so much, but more in memory. So this is audience participation time. First, what U.S. president is on the U.S. penny? Okay, good. It was late in the day, but that wasn't all that great. All right, and now the question is, which way is Lincoln facing on the penny? So how many of you think Lincoln is facing to the right?
You're right, John.
How many think Lincoln is facing to the left? Okay, I know there's a lot of uncommitteds here, but definitely a clear majority for the left. Well, you're below chance on that. Lincoln is actually facing to the right. Okay. And there are lots of demonstrations that could be done like that. This is an example from an old study carried out in the 70s where people had a great deal of difficulty with this task. And we can see mirror image confusion with a variety of other sorts of stimuli, including these simple shapes, and it turns up in lots of different creatures, including rats, pigeons, and octopuses. Well, what I want to suggest is that mirror image confusion is an important clue about how the visual system is representing orientation, because we need to ask ourselves, what are these representations like, such that they should be prone to this type of error. And so that brings me to the theoretical perspective I want to suggest. So if we think about how to represent the orientation of an object, like this knife here, the knife doesn't have any orientation in and of itself. It only has an orientation relative to some extrinsic frame of reference, some frame of reference outside the object. And so we can imagine a frame of reference, a simple frame of reference defined by an up and down direction, a vertical direction, and a horizontal direction. So the knife has an orientation in that frame of reference. And I should say here that I'm going to be talking about two-dimensional representations, although the approach can be extended to three. And what I want to suggest is that representations of object orientation in the brain relate an extrinsic frame of reference, like I've talked about here, but also to an object-centered frame of reference. We've already heard of object-centered representations mentioned earlier today. All right, so what exactly do we mean by an object-centered frame of reference? Let's see here. What I'm going to assume is that both the extrinsic reference frames, which I've already mentioned, have virtual axes that define them, that this is also true of object-centered frames of reference. So that I'm going to assume that an object-centered frame of reference has a principal object axis, along, in this case, the elongation of the knife, and also a secondary axis perpendicular to it. The notion of a principal object axis goes back many years, most famously discussed by Marr. And also that when we're going to define these frames of reference, we need to differentiate the ends of the axes. We need to assign polarity to these axes. And I'll assume that that can be done on the basis of the object geometry, basic properties of the object. So the principal axis might have an end that's designated as pointed and another end designated as blunt. Whereas the secondary axis here, perpendicular, we could also define that in various ways, maybe the curved side of the object versus the straight side of the object. Okay. Now these representations were originally posited for representing object shape for purposes of recognizing objects. What I want to suggest is that they are also central to representing object orientation as well as location, although I'm not going to discuss that. Now, it's important to understand that these representations are object orientation invariant. They don't carry any information about the orientation of the object. They're defined solely within the object context itself. I had to show it to you in a particular orientation, but it doesn't carry orientation information. Okay, so now we're ready to talk about how we could represent the orientation of an object relative to some frame of reference. And I want to argue that these representations are compositional, which means they're made up of separate components each of which specifies some aspect of the object orientation. So that what we need to do is represent how the object axes are related to the extrinsic axes. One thing we need to do is represent how the object axes are tilted relative to the extrinsic axes. In this case, tilted about 45 degrees clockwise. And so, more specifically, I would assume there are two components making up the tilt representation. A magnitude component that says how big the angle is, and it's about 45 degrees here, as well as a direction component. In this case, it's clockwise. Now, this is crucial information for representing the orientation of the knife, but it's not quite enough because the tilt information alone is consistent with all these different orientations of the knife. So we need to do something more to pin down that orientation more specifically. And what in particular we need to do is understand how the ends or poles of the object axes map onto or related to the poles of the extrinsic axis. So for example, we could represent that the pointed end of the object's principal axis is toward the up end of the vertical extrinsic axis. And that's good. I'm going to call this polarity correspondence between extrinsic and object poles. So we could say that for the principal object axis and the vertical axis, the pointed end is toward the up end of the vertical axis. All right, that is helpful because it rules out these two orientations in which the pointed end is down, but it still doesn't distinguish between these. And to finally specify the orientation, we also need to indicate how the secondary object axis here is related to the extrinsic axis. In this case, I've illustrated one way of doing that, which is to say the straight end of the secondary object axis is toward the right side of the extrinsic horizontal axis. And at that point, we now have specified fully the representation, the orientation of the knife in two dimensions. Okay, so this is all very nice perhaps, but is there any way we can make contact with empirical evidence about how orientations are actually represented in your head? And what I want to suggest is that we can do so by looking at orientation errors. And the critical assumption here is that these errors occur when there's some failure in creating one of these orientation representations, or remembering it over time, or processing it in some way or another. And so some parts of those representations could be degraded. And therefore, that the errors can offer us insights into the underlying representations. So what I want to do now is to step through the various things that could go wrong with these representations, and then what kinds of errors we would expect. And I'm going to risk death or dismemberment in order to do this. Fortunately, the front row is kind of cleared out here, so most of you are not at great risk, but you know, Jacob, I don't know. If I get a little too expressive, that could be a problem. All right, so first, one thing that could go wrong is that there could be a problem with the tilt part of the representation. So, you know, if you're supposed to be representing it like this, and you look at this knife, and then a few minutes later I ask you how it was oriented, then you may not fully remember what you originally encoded. So perhaps, for example, you remember most of the orientation, but you forget the direction in which it was tilted. And so if you then have to reconstruct the orientation, you might get lucky and assume that the tilt was clockwise from the vertical, but on the other hand, you might get unlucky, in which case you would represent the tilt as being the correct 45 degrees, but in the wrong direction. And in that case, you might make a tilt direction error. Perhaps more likely is you could have a problem with the magnitude of the tilt. Your recollection of that may be a little bit fuzzy. There may be some error in it, so that you may know the direction the object was tilted, but not be quite sure about how much it was tilted. And in that case, you would make a tilt magnitude error. Okay. So the tilt direction is correct here, but it's not tilted quite enough. All right, from our perspective for today's purposes though, the more interesting errors can occur when you have trouble with the polarity correspondences, with how the poles of the object axes are related to the poles of the extrinsic axes. So suppose, for example, that you have trouble with the relationship between the principal axis of the object and the extrinsic vertical axis, and you forget how that was situated. You could get lucky and reconstruct it correctly, but on the other hand, you could make a mistake in which you mistakenly assume that the pointed end of the knife was toward the down end of the vertical axis. In that case, when you have a problem with the principal axis, you will end up making an error that takes the form of a reflection across the secondary axis. Right, good. So far I haven't cut myself, so I'm ahead of the game. All right. However, another thing that could happen is you could have trouble with the relationship between the secondary object axis and the horizontal extrinsic axis, forgetting that. And if you forget that and get it wrong, you will end up flipping the object across its principal axis, like this, okay? Because you will end up mistakenly representing the curved end as being toward the right instead of the straight side. And that I'm going to call an object principal axis reflection error. So it's a reflection across the principal axis. All right, so far I've told you about two categories of errors. There are some rotation errors that involve simple rotation of the object within the picture plane. And there are also reflection errors in which the object is reflected across one of its own axes. So let's look more at reflection errors. These are the ones I've talked about so far, the object axis reflections, where the reflection is across one of the object's own axes. But there are other kinds of reflections we can imagine. In fact, there's an indefinite number. But two of the more prominent ones are that we can imagine the object being reflected across one of the extrinsic axes. So if this object is reflected across a vertical axis, it will end up looking like this instead. Or it could be reflected across a horizontal axis, in which it would end up looking like this. See? This is not going to end well, I can tell you. All right. Okay, so the object axis reflections I've already described, I said, we would expect those to result from errors in relating the object-centered frame to an extrinsic frame. And these extrinsic axis reflections, I'll suggest, will occur if there are errors in relating one extrinsic frame to another. So let's talk about that. So visual processing on pretty much everyone's account, it requires frequent transformations from one extrinsic frame to another. So for example, you may represent something relative to yourself, but also need to represent it for some reason relative to the environment, like where something is in the room relative instead of where it is relative to me, so that its location remains constant in that representation even if I move. Or there are cases where you need to deal with perspective shifts. This is something I have trouble with giving this talk, because I'm looking at the knife up here and I'm trying to arrange this one so that it looks the same to you as that one up here, and that goes beyond my capacity for spatial thinking. These transformations require specifying the relationship of one extrinsic frame to another. More, very specifically, the orientation of one extrinsic reference frame to another. So let's just take one example. So let's say that I've represented this knife relative to myself, and so that the extrinsic axis is, say, a vertical axis defined by my vertical body axis, the head at the top and the feet at the bottom, and the horizontal axis by left and right for me. And I want to transform that into an environment-centered representation, where I'm representing relative to where it is in the room. Imagine I'm just wanting to represent this picture relative to the room. Now I got lucky, it turns out that this room actually does have a door over there and a window over there. Go figure. And so what I need to know is how I should represent this object center frame of reference in an environmental frame with a horizontal axis defined with a door end and a window end, and a vertical axis with a ceiling and a floor end. Okay? And so to do that, I need to map the egocentric frame onto the environment center frame. I need to represent how the axes of one are related to the axes of the other. This is a relatively simple case. I'm going to assume the axes are not tilted relative to one another, but we could certainly represent that. Here it's reasonably simple. I should map the head end of the vertical axis of the egocentric frame to the ceiling end of the environment-centered frame's vertical axis. And I should map the right side of my body axis to the window side, at least if I'm facing this way when I'm doing it. And then once I've done that, well, what I've done is establish these polarity correspondences just like we were talking about before. Given that I've done all that, then I can correctly place this object in the environment-centered frame. And so, presumably our brains are doing these things all the time when we're transforming from one reference frame to another. However, something could go wrong in those mappings, and we could end up getting reflections of objects across extrinsic axes. So suppose that when I'm trying to do this, which could easily happen, I correctly represent the head end of my body axis being related to the ceiling end of the room X vertical axis, but that I mistakenly map the right side of my body's horizontal axis to the door end of the horizontal axis for the room. So in other words, I set up an incorrect polarity correspondence here. That will end up having me place the knife incorrectly within the environment-centered frame such that it's reflected across the vertical axis. So it'll go from like this to like that. And so that is an extrinsic vertical axis reflection. That's how it could occur. And by similar logic, if I'm foolish enough to make a mistake in which I map the head end of my body's vertical axis to the floor end of the environmental axis, then I will end up making an extrinsic horizontal axis reflection. Like that. Okay, that's a lot of reflections. So those are now 4 types of reflections: 2 object axis reflections and 2 extrinsic axis reflections. It's important to note that when people talk about left-right mirror image confusion, to the extent that they really think about or say what they mean, what they have in mind is an extrinsic vertical axis reflection across a vertical axis so that left and right are flipped. Okay, so far so good? You're still awake? All right.
So, quick
Let's
question.
take a look now
Quick
at
question.
the evidence. Yes, no, I'm going to ignore your question.
I notice on the knife
Uh-huh.
that this is a 3D object that if you reflect it in an actual mirror, you can still rotate it so it's the same as its reflection. So does things change if you have a 3D object that doesn't have that property?
Yes, well, as somebody mentioned earlier, of course, sometimes these objects are not the same on both sides.
Right,
So if there's
exactly.
something that's rotated in 3 dimensions, you see something you hadn't seen before. So there definitely are additional complications that come in when you are working in 3 dimensions. And of course, what I've talked about here as a reflection out of the picture plane could be described also as a rotation around an axis, in 3 dimensions. So, yeah. So I think we could still define the various types of errors that could occur in terms of errors with particular parts of a representation. If the object is different on visible and non-visible sides, and you knew that, then that would bring an additional factor into play. Presumably, you would not make an error where if you knew this object was very different on the two sides, where you would confuse this side and that side simply because. Okay, let's look at some evidence now. And the studies I'll talk about at this point were done with Emma Gregory, who was a graduate student in my lab at the time. Now, there's been a fair amount of research on orientation errors, but for the most part, the stimuli that have been used haven't been adequate for distinguishing all these different types of errors that I've been talking about, and it includes some of my own studies. So when I was studying AH, I used stimuli like this, and as we've seen, when she was asked to copy this while she was looking at it, she drew this. And we're inclined to call that a left-right mirror image error. And indeed, it does take the form you would expect from a reflection across an extrinsic vertical axis. The problem is, though, that that same error could equally be described as a reflection across the picture's principal axis if we assume the picture has an axis here. And so we don't know which of these descriptions of the error reflects the underlying representations and processes. The problem here is that the object and extrinsic axes are confounded. They're aligned. And so we can resolve that problem pretty straightforwardly by using stimuli that have object axes tilted relative to extrinsic axes, as I've been illustrating all along with the knife. In this case, an object principal axis reflection takes a different form than a reflection across the vertical axis. There are other issues as well with types of stimuli that I don't need to go into here. All right, so Emma Gregory and I looked at orientation errors in neurotypical adults. We showed them pictures of objects, the knife that you got tired of seeing, and all sorts of other objects like that as well. And after looking at the object, they were asked shortly thereafter to remember the orientation. And we compiled over a large number of subjects the frequencies of various types of errors. Don't worry, we're not going to go over all of these. Some of these types of errors are reflections, object axis reflections, extrinsic axis reflections. There are also rotation errors, which we categorize in bins of 45 degrees. And then there are some mixed errors that involve both rotation and reflection. These are probably occurring when the participant just didn't remember the orientation at all and simply had to guess. And so you see this is kind of a baseline rate for not remembering anything at all. I'm going to focus on the reflection errors here. And I think you can see that by far the most common type of error was this object principal axis reflection. And once you get an object like this, it's remembered as being at this orientation instead, illustrated there for the column. In contrast, the extrinsic vertical axis reflections, reflection across an extrinsic vertical axis, this being the kind of error you would expect to occur very commonly if the description of mirror image confusion is correct. It is a tendency to confuse left-right mirror images. That occurred very infrequently, and indeed probably not much above that baseline rate of just not remembering the orientation at all. And I will say that we tried in various different ways to get more of those errors and really don't see it. Although interestingly, children do make them in addition to these. But I'm not going to go into that. All right, so just to remind you, we are assuming that these object principal axis reflections are occurring when there's a problem remembering the relationship between the secondary axis of the object, the axis in this case going here, and some extrinsic axis. And for these types of objects, I think it makes sense that this might be a little difficult to remember. The two ends of the knife, the pointy end and the blunt end, or the blade end of the handle, they're very different from one another, probably making it easy to remember which way they were oriented relative to the extrinsic axis. These two sides of the knife are not all that different. I mean, they're different in important ways, but it might be difficult to remember which way they were facing. If we use different types of objects where this difference is very salient and this difference is less salient, we find a lot more reflections this way and not this way. All right. So, why then have people tended to assume that mirror image confusion involves these types of errors, the extrinsic vertical axis reflection? I think just for the reason we talked about before, that object axes tend to be presented in alignment with extrinsic axes, so that what looks like an extrinsic axis reflection may also be an object axis reflection. Indeed, it probably is. Okay, so yes.
So for the stimuli you're using, it seems that there's a strong bias in terms of functionality of the object. It's like the knife won't cut if even though it looks very similar the other way, and the same for the comb and other things. Do you think you would get the same results if you show this participant a novel object with no preconceived functionality whatsoever that has these type of different rotational symmetrical properties?
Yes, we have actually done that. We in the experiment I just very briefly mentioned, we used artificial objects in which we made the differences, the polarity of each axis either very salient or very non-salient simply by manipulating the size of the features on the end. These were completely nonsense objects if people had never seen them before or anything like them. And we see the same patterns of errors, and we can manipulate the relative frequency of reflections across this axis or this axis depending upon how prominent we make the differences between these various object poles. So it's not just because of the functionality. We ended up using a lot of things that are utensils or tools because we needed objects with several properties. We needed them to be asymmetric in 2 dimensions, but we also needed them not to have a standard canonical orientation, such that it was okay to see them at any orientation. Another reason I think we tend to have had findings leading people to believe there's reflections across over a vertical axis was people tended to use objects, or scenes really, that have a standard orientation. And if I present you, say, a coffee cup with a handle, sitting upright like this, there are only a few errors that are plausible for that. You could turn it around this way and it's still at a reasonable orientation. But if you turn it like this, it's upside down, and as long as you know I haven't presented you any objects that are upside down, you're not going to make that kind of thing. So we are trying to avoid placing those constraints. All right, I need to move along. So we wondered at this point, well, what about with AH? At the time I had worked with her before, I hadn't thought about orientation this way. We hadn't done this type of test. So Emma and I went back to her when she was now 37 years old and asked her to do some tasks with these tilted asymmetric objects. And just asked her to do a direct copy task, again, showing her a picture and asking her to make a copy while she's still looking at it. And we found first that she made the same sorts of mistakes that neurotypical individuals make in memory, she made in perception. So here, this is an object principal axis reflection. She's reflected the hammer across the long axis here. This is an object secondary axis reflection. And so that tells us that in perception, she is impaired in relating object-centered reference frames to extrinsic frames. But she also made lots of extrinsic axis reflections, which normal individuals don't do even in memory. So this is a reflection of the hatchet across the vertical axis, a reflection of the brush across the horizontal axis. And this suggests that she's impaired in relating extrinsic frames to one another.
Do you have a driver's license?
Yes, she does. We'll talk about that later. But in addition, we noticed that she made some very interesting errors of relating the parts of objects to one another. So here are 2 examples where, in this case, she's got the overall orientation of the handle correct, but she's reversed this hook jaw along its principal axis, on its presumed principal axis. And here she's got the, she's flipped the handle of the object. relative to the rest.
Okay. And how, if you repeat this experiment with her multiple times, will she make the same kind of?
Well, on any given object, she may get it right once and wrong another time, or wrong different ways. She will make the same overall distribution of errors over time, but it may be on different individual objects. Okay? Yeah. All right, so we wondered maybe she has trouble perceiving the shapes of objects. I had tested her before on object recognition, and she had done just fine. But if you see the various parts of an object, you can usually tell what it is, even if you may be mistaken about how they're arranged. So in this task, we showed her several types of pictures. One, actual objects that are just fine, normal. Chimeric objects in which we combine parts of two separate objects, like here it's the body of a swan with the head of a snake. And part reflected objects where we rearrange the parts within the object such that we reflected some part relative to the others. There were 26 of each type of object, and we tested control participants. They did just fine on all of these. AH got all of the normal ones right. She said they were fine. She correctly rejected all the chimeric ones. She said, no, those are not right. Yet for the ones who were reflected apart, she only detected a problem with 13 out of 26. And here are a few examples of objects she thought were just fine. So this bear is going to have trouble walking, but she thought it was okay. The umbrella she thought was okay. And this one is particularly strange. She thought the tiger with the head upside down was particularly good. And this, I think, has some interesting implications. I think object part orientations, like whole object orientations, are probably represented as relationships between reference frames. This is something a slightly different way Jacob was talking about the need to do part analysis and relate the parts to each other. So what I want to suggest is that for a complex object, there's probably an overall set of object axes, say top, bottom, front, rear for the bear, and then the major parts themselves have axial representations. And the way that we represent the overall shape of the object is to map the part object-centered frames, or the part-centered frames, onto the next highest level, and ultimately up to the entire, or the main object-centered frame. And we need to do this in exactly the same way as I've talked about before, location orientation representations for parts relative to other parts. And what this result from AH suggests is that her deficit affects object part as well as whole object orientation representations, and suggests there's some continuity between the representations for whole objects and for object parts, which I think is an interesting consequence. All right, I don't think I have a lot of time, but I would like to tell you just a little bit about one final set of studies done with my graduate student Peng. So far, I've been kind of talking as if, yes?
Maybe if you ever showed AH objects in the actual physical object, what kinds of errors?
She still makes errors with them in 3 dimensions, yes. So they don't have to be 2-dimensional pictures. She makes errors, say, in trying to pick up objects off the table because she'll reach the wrong end of it or even reach the wrong place. She routinely has little cuts all over her hands because when she's working with kitchen knives, she sticks them up by the blade.
And she had an MRI?
Yeah, she has had an MRI. There's nothing clearly, this is a developmental deficit. It's been with her all along. There's clearly something that's not right somewhere in her brain, but we don't know exactly what. We recently did some fMRI with her, and we're trying to figure out what's going on.
Most of the objects that you talked about were manipulable.
Yes.
If she sees big objects which have all structures, door handles and
Very large, yeah. Well, I know at least anecdotally for her that she makes errors with large objects or distant objects as well. She certainly has trouble with telling time, and she would tell me about problems she had looking at the clock tower on campus and seeing the hands in the wrong positions and orientations. So, now, I can either answer these questions or do the next little part of the talk. What should I do? It's getting late, so.
5 minutes?
Yeah, let me try. Okay, I would like to tell you about this. So I'm going to try to do this briefly. I've been taking for granted so far that it's straightforward how we assign axes to objects, and as Jacob talked about, that's not at all true. So I've assumed here that the knife has axes like this, and researchers have assumed that object geometry is important in doing this. Particularly elongation has been noted. But there are lots of other factors that could come into play, including symmetry, which we've heard a little bit about. And even if we think elongation may be important, or if we think that, well, let's just stick with elongation, there are various different ways we could conceivably construe elongation. So the object has an elongated handle, so one thing we could say is, well, because of that handle being elongated, this would be the principal axis for this hatchet. On the other hand, there are reasons to think that perhaps the overall shape, the global shape of the object is taken into account when axes are assigned to the object. So this is the axis of least second moment, which minimizes the sum of squared distances of points in the object to the axis. That's been mentioned as a possibility. Another that's been discussed is the longest span axis, the longest line you could draw between 2 points in the object. And so how do we decide, or can we decide, well, what actually happens here? And what we were thinking is that given that we know that reflection errors tend to occur across object axes, then we can use the object axis reflections to infer where the object axes are. That, in essence, we take objects like the handle, pictures of them, present them to people, see what reflection errors they make for them, and then that will tell us where the axes are. All right, so we present objects at any given orientation. We present people with a probe object at a random orientation, and their task is to adjust that probe to match the target shortly thereafter. And so here's one possible answer, not terrible, but it's not really great. And then what we did was just analyze all of the reflection errors, errors where the object has been reflected anywhere or another. And the way we looked at them is, so if we take the target stimulus and the response with the reflection error, we can superimpose those and easily compute the axis of reflection. And then we want to be able to combine data across all the different orientations in which the object was actually presented. So we code the reflection axis relative to a normalized target orientation. So take this one, say upright, and then we will code that as the reflection axis and then plot it like this. We collect a whole bunch of reflection errors and then just plot them. Quickly, we first did this with the simple sorts of objects we'd used before, thinking that we knew what we would expect to find. And here's what we find. So just as we would expect, each of these black lines is a reflection axis, and they're clearly clustered around 0 and to a lesser extent around 90 degrees, suggesting that that is the principal axis of the object, is as we would expect through the main elongation, with the secondary axis perpendicular to that. All right, the interesting question though is what happens if we use more complex objects. So we took a bunch of objects with something protruding from the top of the elongated part. And what do we expect to see? Well, if the principal axis of the object was defined to coincide with the elongated part, we expected the axes to cluster at 0 and 90 degrees. 0 degrees simply because we defined the normalized orientation to coincide with the elongated part. If the global shape axes were how the principal axis was defined, then we expected the reflections to be tilted away from 0 degrees to lesser or greater extent in the direction of the protruding part. Real quickly, what we found was that the axes that we observed as reflection axes were very closely aligned with the axis of elongation of the handle here, the elongated part more generally, and again a perpendicular axis. And so our conclusion was the object principal axis was defined on the basis of the elongated part. Now we can use this procedure with other sorts of objects, looking at other sorts of properties as well. All right, to wrap up, these are just what I said before. The brain's visual system is using coordinate system representations constructed around axes and representations that map coordinate systems onto one another. And errors can offer windows into these representations, and at the same time help us understand the errors that we made. And thanks for your patience.
Peter.
So I'm well known as being terrible at distinguishing right and left, but I'm very good at distinguishing compass direction, northeast.
Okay, I'm the opposite.
Okay, so
I
anyway,
am
that's
totally
not,
solid on that.
but, so I remember reading a little while ago about a group in a language from Australia, Northern Australia, where they don't have words for right and left, even in their language, and they do everything in terms of compass direction. So one wonders how your studies might be impacted by that
Well,
where it's not universal.
No, it's
all
very
humans do.
interesting. The spatial language, there are languages of a group that lives in a hilly country where some of the main directional terms are uphill, downhill, stuff like that. I would expect, though, that mental representations, I don't think these are language-based representations I've been talking to you about. I would strongly suspect that these people in Australia still have mental representations that differentiate the two sides of their bodies, and that they probably use those in representing locations and orientations of objects relative to them. That's an empirical question.
I don't know. So.
Yeah.
You probably know of dyspraxia, which is a neurological disorder of tool use. And the way it instantiates itself is that people are not able to imagine, say, using a toothbrush, and they do all kinds of weird things. So has that been investigated as a erroneous representation of the geometry of the object, or would you put that into a different disorder?
Well, any kind of symptom like that could conceivably occur for lots of different reasons. And maybe some people who are having that kind of problem are having difficulty remembering the shapes of the object and how it's manipulated. Given what I know about that, that's not probably likely in all of the cases. For example, one of the ways it manifests is that if you're asked to mime brushing her hair with a brush and you should do something like this, well, they kind of use their hand as the brush, and that's considered an error. That doesn't seem to me to be too likely to be the result of some difficulty with remembering how to represent the shape. But that's just speculation. But no, as far as I know, that type of impairment has not been investigated. Okay, I think this is a good time to stop.
Okay, great. Thank you very much. There is a reception upstairs which will continue for as long as people have energy.